Welcome back to Algorithmic Game Theory. In the last lectures, we've introduced the notion of a Bayes-Nash equilibrium and also the notion of a smooth mechanism. All this was to analyze non-truthful mechanisms. Today we're going Welcome back to Algorithmic Game Theory. In the last lectures, we introduced some tools to understand non-truthful mechanisms. Namely, we introduced Bayes-Nash equilibria, we introduced smoothness of mechanisms, and all this was about understanding what happens if a mechanism is not truthful, so it's not in the bidder's best interest to just report the true value. Maybe it's even impossible to report your true value. What can we then still say about the outcome of such a mechanism? Today, we'll be a little more specific about the application, namely we'll consider combinatorial auctions. And for combinatorial auctions, we see two different mechanisms for which we will then, in both cases, be able to show that they are smooth, and via the result from the last lecture, this immediately implies a bound on the price of anarchy for Bayes-Nash equilibria, but also for other equilibrium concepts. Before we get there, let's first recap all these definitions. So we are considering a combinatorial auctions, which means we have n bidders or players, which we'll call capital N. So they will be numbered 1 through n. And we have m items, capital M, 1 through m. Each of the bidders now has a private valuation function which maps subsets of the items to non-negative reals. I realize that I'm always dropping our convention that we're following all the time, namely that this is a monotone function, getting more items will never hurt you, and also that getting no items, you have a zero value. So this is all implicit in whatever we're doing regarding combinatorial auctions. Now we're trying to find a mechanism, which is a pair of an outcome rule and a payment rule. Both take as their input a bid profile. And then the outcome rule determines an outcome, which means an assignment of the items to the bidders in the case of a combinatorial auction. And the payment rule defines how much the bidders will have to pay. And also this time we are still assuming that the bidders will always pay something non-negative. But as you see here, these mechanisms are not necessarily direct mechanisms, because these bid profiles, the respective bids, those are not necessarily valuation functions. And as it turns out, our first mechanism today will be an indirect mechanism. The second mechanism that we will be studying today will be a direct mechanism. And then what was it that made a mechanism smooth? We call a mechanism lambda, mu smooth if the following holds. Take any vector of valuations, so a valuation profile, and take now any player. Then there has to be a safe deviation bid for this player, which now fulfills the following. For any bid profile B, we have that this inequality is fulfilled. Take the sum over all bidders. What is this bidder's utility when this bidder is unilaterally now bidding bi star, whereas the others are bidding b minus I? This should be at least lambda times the optimal social welfare minus mu times the sum of the payments under B. And this implies that the price of anarchy for base Nash equilibria, for coarse correlated equilibria, for correlated equilibria, for mixed Nash equilibria, for pure Nash equilibria is always bounded by the maximum of mu and 1 divided by lambda. So all we are doing today is just proving smoothness of mechanisms. And this is then has the immediate consequence that we are also bounding the price of anarchy using the proofs from last time. Good. So the first mechanism I'd like to talk about is item bidding. Namely, what will we be doing? We will now be selling each item in a combinatorial auction separately. And we ask, how good is this? So the one way you can think about this is kind of a parallel eBay auctions. Maybe you just want to buy one phone, but you cannot actually tell eBay that you only want one phone. If you buy all of these auctions, if you win all of the auctions, then you're buying suddenly multiple phones. And this is why this is a non-truthful mechanism, because you cannot even reveal your true preferences. So this is an indirect mechanism. The bids that you're posting, those aren't actually your true valuations. Let's see how we could design this and how we could express this more formally. So what is item bidding? We are actually just selling each item in a separate first or second price auction. Here we're now doing this in a first price auction just because it's easier. So what will this look like? Each bidder I reports a bid Bij for every item. And then each item is allocated to the bidder with the highest Bij, and all bidders pay the sum of their respective winning bids. So if it so happens that you now win 10 items, then you also pay for all these 10 items and you pay your bids. Good. So this is not a truthful mechanism for many reasons. It is easy, but it is not truthful. Why that? Well, first of all, we have this weird payment rule, which even for a single item would be a first price auction, which we know is not truthful. But other than that, also, this way of bidding, this cannot be truthful because you cannot tell the mechanism what you really want. You do not report your true valuation functions, but all you can do is you can bid on a single item. Not on a single item, but you can bid on all items, and then you might also win multiple items. And the kind of valuation functions we now want to analyze this with our unit demand functions, which I hope you remember, in which you actually only want one item. So recall how they are defined. We'll have unit demand variations, which mean that Vi of Si is the maximum of all j and Si, Vi, j, for Vij being just non-negative numbers. For example, all these Vij might be equal to 1. Then you don't care which item you're getting. You always have a value of 1 when you get at least one item. But even if you get 10 items, your value will still be 1. And this feels that with this auction format doesn't mix quite well, because in this auction format you cannot actually express this. In this auction format you say, okay, if I bid now something on this item and on this item and on this item, and it might not happen that just I'm winning all of them. And I couldn't just say, okay, believe me, I only wanted one of them. Good. But does this still give us a good mechanism? Yes, it does, in a way that this is still a smooth mechanism. And this way we get a bound on the price of anarchy. For unit demand valuations, item bidding with first price payments is a half, 1 smooth. So this means we get a price of anarchy of at most 2. And this holds for base Nash equilibria, coarse correlated equilibria, mixed Nash equilibria, pure Nash equilibria, all at the same time. We don't have to prove this for every single equilibrium concept, but we only have to prove smoothness. Good. How do we prove this? Maybe let's first recall what the smoothness definition wanted from us. Okay, it wants lambda and mu. We now have lambda and mu. Lambda is a half, mu is 1 in our case. And now for every valuation profile, the valuation profile will be fixed. We'll now have to define for each bidder this bid bi star, which has this property, that the sum of the utilities when this bidder bids bi star, the other bidders keep bidding. This is at least lambda times the optimal social welfare minus mu times the sum of the payments. And in our case now, this looks as follows. Consider the welfare maximizing allocation on V and let Ji be the item assigned to bidder I, without loss of generality, of course, they are getting only a single item. And we let j subscript I be 0 if I does not get any item. Good. Now, how do we define the deviation bit from this? Maybe you should recall how we did this for the case of the all pay auction. How did players bid there? What was our choice of a safe bid there? We said, okay, the one who's supposed to win the item should bid a constant times their value, and the ones who are not supposed to get the item shouldn't bid anything. And this is exactly the kind of a rule that we are again using, namely, we now define Bij to be Bij over 2 if j is equal to ji and 0 otherwise. Which means every bidder is now bidding half their value only on the item that they're getting in the optimal solution and nothing on any other item. You should observe that this immediately makes sure that you're not getting more than one item. It might not be happen that you're getting no item or that you're getting the item that you're supposed to get in the optimal solution. And this is exactly why this now works out. What do we now have? We now have that the utility when bidder I deviates to bi star, the others keep bidding b minus I, and the value is vi. This can be, okay, either I get my item, and when will this be? This will be if the maximum other bid is smaller than what I'm bidding, or my utility will be 0 if I'm not getting the item. And what you can see here is that regardless of what is happening now, this will be at least vi over 2 minus the maximum of bi prime comma ji. Good. Now we can also include in this maximum here bidder I. That can only increase the maximum. Now take the sum over all bidders. What is it that we're getting? Well, we are getting, I forgot the subscript I for the j here. We are getting the sum of all these vi, ji over 2 minus sum of all these maxima. Now, how much is this? We are taking the sum over all bidders, and then we take the value they have for the item that they're getting in the optimal solution divided by 2. So this will be exactly a half times the optimal social welfare. And what do we know about this part here? Here we are taking the sum over all bidders, and then we ask this item that this bidder is getting in the optimal solution, what's the maximum bid on this? And instead of saying this in this super complicated way, we might as well say, what's the sum of all maximum bids? So technically this can also be this could also be a little different because not every item needs to be allocated in the optimal solution, but it is clearly upper bounded by the maximum, by the sum of the maxima of all bids. And this is nothing but the sum of the payments in our mechanism. So overall, this will be at least a half times the optimal social welfare minus the sum of the payments. And this is exactly what smoothness requires from us. Excellent. So we already have our first simple mechanism for combinatorial auctions. For unit demand combinatorial auctions, we now see that via this first price item bidding, you will have a price of anarchy of at most 2. What we'll do next is we'll have another look at these greedy mechanisms, which we saw earlier, which will be truthful if we use these threshold payments and in a single parameter setting. Now we are not considering them in a single parameter setting. We're not using these threshold payments either, but rather first price payments, and then we will again show not truthfulness, but smoothness. Now I'd like to turn our attention to a greedy mechanism, which is indeed a direct mechanism. So bidders can actually report their true values, although they won't want to, because one reason being that we are using first price payments. So what does this mechanism look like? So bidders report functions BI mapping from the power set to the of all items to the non-negative reals. And our mechanism is now first thing is to collect the bids. Then we'll sort pairs I, S by non-increasing score BI of S divided by the square root of the size of S. and then go through this sorted list and assign S to I unless the player has already been allocated bundle, or one or more of the items have already been allocated. And finally, we let Pi of B be the bid that bidder I had on the set S, where S is the set of items allocated to bidder I. So you might remember the greedy by value algorithm mechanism, or greedy by square root value density. I mean, that worked more or less the same way, except for the fact that, well, their bidders were single-minded, so we actually only had to order the bidders. Now we'll have these pairs of bidders and sets that we might give them, and we now order them by this non-increasing score. How much are they bidding divided by the square root of the size of the set. And we'll go through this sorted set of pairs, and we'll turn this into an allocation unless this bidder has already received something before, or one of the items we have already allocated. And then we just don't do this in a super smart way this time. We just say that, okay, you are just paying whatever you bid on the set that you're winning. We already know that this algorithm we couldn't actually implement truthfully, because even if we had now unit demand bidders, then this would be actually the greedy algorithm that just gives an item to the one who bid most and then continues like this. So while there is still a bidder who has not received anything and an item that is left, take whatever match gives you the highest greedy increase. And we know that this couldn't be implemented truthfully, but we're not even trying here. We're not doing this even in a very smart way. We're just saying, okay, just pay what you're bidding on this set. So certainly, even if you have only a single item, this will not be a truthful mechanism, because it will just be the first price auction. Nonetheless, we can show that this is actually a smooth mechanism. Namely, this is a half comma square root 2m smooth. Good. How do we prove such a theorem? What do we have to do again? We again have to say, okay, there are good deviation bits. What might those be? How did we do this last time? We considered the social welfare optimum, and then this social welfare optimum led us to a good bit. And we'll do exactly the same thing here again. So what we'll do is we'll let x1 star through xn star be an allocation that maximizes social welfare. In other words, opt of v will be equal to sum of the vi of xi star. And what will our deviation bits now be? bi star we let it be the following function. Bi star of s should be vi of xi star divided by 2 if s is a superset of xi star and 0 otherwise. So what we're doing here actually is we're defining single-minded bits. We just let this safe deviation bit, we again let be something that, okay, try to buy what you're getting in the optimal solution. And now this means this will be actually a single-minded bid. Just bid on the set of items that you're getting in the optimal solution and nothing anywhere else. And this is expressed by exactly this bid. To make it monotone, we're not exactly bidding only on the item that you're getting in the optimal solution, but also on every superset. That is actually something that you might be arguing here whether or not you want this. But once again, the structure is again bid on the set of items that you're getting in the optimal solution. And then we will now have to see how much will your utility be. Before this was somehow easy because we could say, okay, I'm bidding just on that single item that I'm getting in the optimal solution. Then either I'm getting it or somebody else is bidding on exactly this item. Now here things are more complicated because it's not that other bidders are bidding then on exactly this set of items, but only more, but they might be just bidding on other items and items that are contained in here in the set of items that we want, and that's why we are not getting it. But nonetheless, we can again see what will happen. And we can write actually the utility that you're getting by in a very similar way that we did this before. We let tau I of s comma b minus I be the smallest bit such that bidder I wins set S against B minus I. This we might call the critical bid. And then we can now say, okay, if my value is more than this critical bid, so my value divided by 2, then bidder I wins xi star in bi star comma b minus I. And what we'll have is that the utility with bi star, the others are bidding b minus I, my value is vi, this will be equal to my value for that set divided my value for that set minus my value for that set divided by 2, so my value for that set divided by 2. Or, if this is not true, then we certainly know that your utility will still be non-negative and it will still be at least half your value for that set xi star minus the critical bid. And that should be the critical bid, of course, for the set xi star. Okay, so what we're getting is that if you now take the sum over all bidders, bidder I is always deviating to bi star, the others keep playing, then this will be at least the sum over all bidders, vi of xi star divided by 2 minus the sum of these critical bids. This first thing here, we again see, okay, this is equal to the half the optimal social welfare. But what we now have to still understand is, how big is that? What do we know about the sum of the critical bits? What we'll do is we'll bound this sum here by we'll bound this by 2 square root 2m times the sum of the bids for the outcome of our mechanism. And this here, the sum of the bids for the outcome of our mechanism, this is exactly the sum of the payments. And if we have shown this, then what you see is that this inequality will be exactly smoothness. So all that remains is actually showing this inequality here. So let's write this down as a separate lemma. We'll fix some bits, and we now let f of b be the allocation of the greedy mechanism and we let x star be another feasible allocation. Actually, x star is our social welfare maximizing allocation, but that's something we don't actually too much care about now, because all we're using that is that this is indeed a feasible allocation. Then the following holds: the sum of the critical payments, critical bits, is at most square root 2m times the sum of the bi of fi of b. Okay, let's understand this. We have here, for every bidder I, we ask, how much would you have to bid on the set xi star in order to win it, when the others are bidding b minus I? And then we sum this all up, and on the right hand side we have some factor and this term here. What's this term? This is just something that we can call, or have also called before, the declared welfare, namely how much is valuation B, how much are the claim valuations in B telling that the outcome that is computed under B is worth. What's interesting about this lemma is that the true valuations actually don't appear at all in here. This is only about the bits. Recall that originally our B star was the social welfare maximizing allocation under valuation profile V, but that's something we don't care about at all when we're stating this lemma. X star is just some allocation. And we now want to say, okay, for any allocation, the sum of the critical bits to kind of unilaterally enforce this allocation, always one player enforces the allocation while the other players are just doing the same that they were doing before. The sum of these critical bits is bounded. And here we are now using the property that we actually use a greedy algorithm and not just some arbitrary algorithm. How do we do this? We let epsilon be greater than 0, but it's tiny. And now, for all I, let bi star be the following function. bi star of S should be the critical bit for the set xi star, comma b minus I minus epsilon if S is a superset of xi star and 0 otherwise. What's that? What's this? What does this mean? Well, there is now this critical bit. This is how much you would have to bid on the set xi star in order to win it. Or you would, maybe it's the infimum because there's these tie-breaking things, but when you're bidding less than this, then certainly you're not getting the set xi star. When you're bidding less, so, and by this I mean just some epsilon less, then you're certainly not getting the set xi star. Good. So when you're bidding this much, you'll end up with the empty set. And now we'll define one more function, namely bi prime of S. This will be the maximum of bi of S and bi star of S. What is now happening? Here I was arguing you're not getting anything. Here now you're actually bidding bi of S, just as before, and then sometimes you also maybe bid more, but you're bidding then this much, but this is never enough. Bidding bi star, as I was arguing before, never got you anything. So that's still true here. Even here, what you get, and this will be something that we'll be proving more formally, when you're bidding bi prime, then you're still getting the same thing as when you're bidding bi, although you're somewhere bidding maybe more on the set xi star, maybe you're bidding more, but you're not getting more because you're bidding below the critical bid. So the point is that even if you bid now bi prime, nothing actually changes. So what we have formally is that f of b will be equal to f of b prime. Why that? Because of the following argument. Suppose f of b is not equal to f of b prime. Then there has to be a pair I comma s such that I comma s is allocated by the greedy algorithm or the greedy mechanism on b prime but not on b, and we consider the first one of these. Then why could this only happen? This can only be happening because I'm bidding now not bi of s, but bi star of s on this item. And by this I mean the first one of these in the ordered list, to be very precise. So it has to be bi prime of s isn't equal to bi of s, which means that bi prime of s is equal to the critical bit for set S under bit profile B minus I. But because this is the first one, and this is minus epsilon, because this is the first pair, the execution so far was identical to the one on B. And what do I know about getting set S in B? Will bidder I get set S when everybody's bidding B with a bid of tau I of S comma B minus I minus epsilon? No, because you have to bid at least this tau I of Si comma B minus I when you're bidding against B to get the set S. So this means that you cannot be getting the set S. So this leads to a contradiction, because everything that was happening so far was actually what was also happening on B, but we know that on B with this bid you're not getting this set. So this means nothing can actually change. One thing that is important at this point is that we are actually using a greedy algorithm. A bidder who's getting something will be excluded after this point. Also, the bids on certain sets we don't care about unless we see them for the first time. And this is a property called loser independence. So everything that we don't see happening around, other than what we're actually currently allocating, this doesn't matter. And this is maybe a little implicit in this proof, that this is using this greedy property, that we are now considering the first one in this ordered list, and everything that happened so far was the same and also didn't include bidder I. Bidder I's bids haven't been looked at so far, and we can easily change them, nothing changes. And this is why we get now that here f of b is equal to f of b prime. Once again, this wouldn't be true for more complicated algorithms which are not as simple as this greedy algorithm. For example, if you maximize social welfare or declared social welfare, then you cannot do these tricks. Good. Now what do we have? We now constructed this B prime bit profile with a property that on B prime actually the same is happening as on B. This is written here in a very fancy way, or not very fancy way, but in a somewhat fancy way. Now what else do we know? We also know that if bi of s is not equal to bi of s prime, then beta I does not bi prime of s, then beta I does not receive set s. This is exactly the statement or the kind of argument that we were doing just before, because if bi is not equal to bi of s prime, then you're bidding below the critical bid, and so you're not getting the items. You're not getting this set. What does this mean? The point is now that the declared welfare that we're getting with B is, well, we're seeing the same allocation as with B prime, and also this outside function we can also change to B prime, because also there this doesn't make a difference. How does this help us? Maybe let's go back to what we wanted to show. This was our lemma that we wanted to show. And we wanted to show that the sum of the critical bits is at most some factor times the declared welfare on valuation profile B. But now we know that this declared welfare on valuation profile B, or on bid profile B, this is just the same as what's happening on B prime. And then what we'll now do is we'll see what does this B prime, what's happening on this B prime. In more detail, the mechanism computes a square root m approximation of the optimal declared welfare. We've seen this for this mechanism for the special case of single-minded bits. There we had even a guarantee of square root m. Now, by just the same kind of techniques, you will see that you're getting a square root 2 times m approximation of the optimal declared welfare here. What does that mean? This means that the declared welfare that we're getting will be at least a 1 over square root 2m fraction of the declared welfare on any other allocation, so in particular this X star allocation that we wanted to talk about. Bi prime of xi star, well, what was that? That was the maximum of bi of xi star and the critical bit for xi star. So, of course, we can just ignore this maximum and say, okay, this will be at least the sum of these critical bits. And so this sum here, we just move out this minus epsilon, then we get minus n times epsilon. Good. What does this mean in total? We now have that this here is actually the right-hand side of what we wanted to bound, and this here, this turns out to be the left-hand side of what we wanted to, of our inequality. And so we are actually kind of done here. So let's combine all of this. We now have that the sum of all these critical bits is at most this sum of these bi prime times of xi star plus n times epsilon. This sum, as we see, will be at most square root of 2 times m times the declared welfare on b prime. And this, as we've seen, is exactly equal to the declared welfare on b. And this holds for all epsilon greater than 0. So in particular, make epsilon as small as you like, you will always see that our statement here is true. And let's go back to our lemma. This here, this is exactly the inequality that we wanted to show, and if it were not correct, then there would be an epsilon for which this inequality does not hold. So this proves our claim. Now let's come back here. We've now shown that this inequality is actually true, and so we've shown that this was actually why we were doing this. We wanted to show that for these deviation bits, some of the utilities when now one player is unilaterally deviating is at least half times the optimal social welfare minus, and then we get, okay, we had this here as the proxy, the sum of the critical bits, and then we could, now we have seen that this is at most this factor square root 2m times the sum of the payments under B. So this proves our claim. Good. So one interesting thing about this is that we did not actually use the precise way that this algorithm works, but only that it is a greedy algorithm. And indeed, this is the way the original paper states this result, that whenever you have a greedy algorithm for, well, greedy, you have to specify what you actually mean by greedy then you can always do this argument, and what you're effectively getting is that always here you're getting just the approximation factor of the greedy algorithm. And so if you take this greedy algorithm, combine it with some payment rule which is like first price payments, so you just pay your bid, then this will become a smooth mechanism with a price of anarchy, which is then bounded by a constant times the approximation factor of the algorithm. Now, the one question that you might now have is, why is it that we are considering only first price payments here? Wouldn't it be much nicer to do this with kind of second price payments? Yes, that is indeed something very reasonable and something that people have studied. And this is true for both this greedy mechanism as well as for our item bidding that we were considering in the first part of this lecture. But there's one big problem about second price auctions. Let's see this. Namely, consider a second price auction Our first bidder might have a value of 1, the second bidder might have a value of epsilon. Now, it is indeed a pure Nash equilibrium if the first bidder bids nothing and the second bidder bids, for example, 1. Because why is this a pure Nash equilibrium? Here, why wouldn't you want to deviate? Let's first consider the first bidder. The first bidder wouldn't want to deviate because they would have to bid at least 1 to win the item, but that means no utility. The second bidder is also happy because they're paying nothing. Although they're bidding this much, this is still a pure Nash equilibrium. Everybody's happy with their choices. So truthful bidding is a pure Nash equilibrium, but it is certainly not the only one, as we can see here. And what we also see is that the price of anarchy is huge. The price of anarchy is like 1 over epsilon, where epsilon we can make as small as possible, as we like. Good. So what can you still do when you want to understand, for example, item bidding with second price payments? You'll have to avoid situations like these, where some bidder is drastically overbidding. Because why would you want to do that? There's actually no point in, instead of bidding your true value, you bid way more than your true value. This is actually a dominated strategy. It is never worse to bid your true value. And similar effects you should also then exploit in, for example, item bidding or such greedy mechanisms with more kind of second price payments, that there might be really bad strategies in which players are overbidding drastically, like in this case, but there's actually no real point of any player any time choosing such a strategy. And if you now make the assumption that players are not overbidding, however this may look in your exact details, so here you just don't bid more than your value, then suddenly you can again do these very nice price of anarchy arguments. But that's the point why we did not consider these second price auctions today, but only the first price variants, for which we could still show show good price of anarchy guarantees. If you have such an overbidding assumption, then you can do the same thing also for second price payments. If you're interested in that, please have a look at the references that you'll find in the lecture notes, where in all these papers it is done for both the first and the second price perspective. Good. So it's time to conclude this overall discussion of non-truthful mechanisms at this point. I hope you've seen that there is a way you can also argue about mechanisms which are non-truthful, and the reason why it is important for me to include this in this class is because it maybe makes you more appreciate all this truthfulness. Because suddenly you realize, okay, truthfulness isn't actually a feature that is nice to have, but it makes it much easier to talk about the outcomes of strategic behavior, because it is just very natural to assume that every player is just reporting their true valuations, and so if we just maximize declared welfare, we are at the same time also maximizing the actual social welfare. If you have any questions, please reach out to me and stay safe. Bye.